Welcome to another exciting episode of CIS 2353. Today we're going to talk about the queue, Deque and Priority Queue implementations in Chapter 11. There's also the Chapter 10 information, which is the queues, deques, and priority queue introduction. So the difference between these is that this one more gives an overview in Chapter 10, and Chapter 11 will do a little bit of looking at. This goes over implementations, but there's a lot of redundancy, and also some of this stuff you can refer to as needed. So mostly we'll probably focus on Chapter 10. So first of all, we got done talking about the ADT stack and the ADT bag before. We know that a bag, you can add information to the bag, also known as a multi-set. You can add information, data to the bag, and there is no real rule about where the data has to go. There's no particular ordering. Order doesn't matter. Stack, the order does matter. First in should be last in should be the first out, or first in, last out. So it's called a LIFO data structure. So we access only items at the top for both adding and removing and peeking, looking at the data. A queue is a little bit different. A queue is another name for a waiting line. Used within operating systems and to simulate real-world events, they come into play whenever processes or events must wait, and they organize in FIFO, first in, first out order. So stacks are LIFO, queues are FIFO. One other thing to keep in mind is a lot of other countries, especially countries that were British colonies that weren't America, use the term queue a lot more frequently than we do. They use queue to refer to standing in a cafeteria waiting for your food and things like that. Instead of saying standing in line, they would say standing in queue. So here's examples of queues. These are be everyday queues. Assuming the ducks would wait one by one. Some birds do kind of follow that pattern. The elements here, this is probably a really good example because they're actually linked. So that's kind of like a linked chain implementation of a queue. And then right here we have the different vehicles going into the car wash. I'm assuming that's an El Camino because it's got a really, really long trunk and a really, really, really short hood. The terminology that you will use with queues typically, we say that the item added first or earliest is at the front of the queue. The item added most recently is at the back or the rear of the queue. So whereas a stack, you can access things only at the top, one location. With a queue, you can access things at the front and the back. So there's two openings. And with a bag, you can access any element, really. You just say, give me one. Okay. Additions to a software queue must occur at its back, and then the client can look at or remove only the entry at the front in a regular old queue. So first in, first out. The terminology used with queues is a little different typically with stacks, although implementation-wise you might see things like push an item into the queue and pop an item from the queue, just like with stacks. You just have to remember the order is different. The actual formal terminology is a little bit different with a queue. So data, without giving an implementation information, remember with an abstract data type, we do not talk about the implementation. We talk about what it's supposed to do, but not how it does it. That's where data structures come in. So a collection of objects in chronological order and having the same data type. Okay, so enqueue, and the UML would look like this. Public method called enqueue. That's how it's pronounced. ENQUEUE. And just like queue, but it has EN in front of it. New entry of type integer, for example, and then void. Dequeue, right here, DEQUEUE. That means to remove an item from the queue. We also have get front, which is kind of like peek with a stack. It returns a reference to the element without removing it from the queue. Is empty and clear are both present just like they were with our bag, for example. Here's what the interface might look like. So once you have this definition from earlier, right here, you can build up the interface, which is our first real move into implementation. So you've got the interface queue interface of type T. So this is a generic public void enqueue. Notice they don't have a body, right? Because all the methods are just headers inside of an interface. They're abstract methods is what we would call them in general. You actually don't, again, need the public here. They do it in the book, but you really don't need it because they're already public. They're public, they're automatically abstract, and you can't, if you put any data in here, that's automatically public, final, and static. So you can't have like instance fields in an interface because you can't create an instance of an interface. It wouldn't make sense. Okay, so here we go. This is a queue of strings. Starting at the top, Jim enters the queue. We're assuming they're coming from this direction. Okay, so Jim enters the queue. We'd say maybe he's being, served by someone up here. Maybe it's a donut shop or, some other food place, because I always like food analogies because I love eating. So Jim is at the front at the McDonald's or the Chick-fil-A, and he's waiting on his meal. And Jess comes in behind Jim. So Jess has enqueued. So we enqueue Jess. And Jim is still at the front. So Jess is now the rear or back of the queue, and Jim is the front. Then Jill comes in, and Jess is no longer the back of the queue. Jill is the back of the queue now because she enqueued. Jim has still not dequeued yet, though. And then finally Jane. Now Jane is the back of the queue, the rear of the queue, and Jim is still the front. Now at any point Jim could have left, like he does here at E, at F, we enqueue Joe on step E here. So we've got Jim at the front, Joe at the rear. Jim leaves the line. Maybe he's done being served or what have you, done with his transaction. Jim leaves, and now Jess, who is behind Jim, becomes the front of the queue. So she's the front, and then Jerry enqueued at some point here. Jerry enqueues at G, so that means Jerry's the back of the queue, Jess is the front of the queue. Then Jess is dequeued, and then Jill becomes the front, Jerry is the back. Pretty cool. Another line or queue of people looks like this. I really hope that little girl is with like one of her parents because she's really way too short to ask for the tickets by herself. Anyway, so he's enqueuing right here. She's getting the tickets. She's probably about ready to dequeue. Hopefully that's her daughter. So anyway, wait line. This would be a CRC card for a simulation. A lot of times when you hear the term simulation, a lot of people think of these big, huge scientific things where a hologram pops up out of a desk, like on Star Trek or Star Wars or Stargate or other star things. But it's not always like that. This is not what always happens. It's not always really cool and interactive and graphical. Pretty much all the simulations I did for my PhD, and they were hundreds of hours of running simulations, they were all done using network connection, console output, and generally that's quicker. When someone needs a different type of visualization, it makes sense to put visual components, but simulations do not necessitate the need for GUI interaction. It's just one other layer you put on top of it to maybe make it easier to use in some cases. Some cases it doesn't. If the only person interacting with it is a technical person who's used to issuing text commands and they're good with that, then you often do not need GUI. So the next thing we have are the responsibilities and the collaborations with the CRC card of the wait line. The wait line will use the queue, so it simulates customers entering and leaving a waiting line, displaying the number of people being served, total wait time, average wait time, and number left in the queue. Collaborations. So this collaborates with a class called customer, so instances of the customer. You have the collaboration right here. If this were one, I think it's in the book on one of the pages. It's a full diagram. The wait line, it's a one to many. So if you've taken CIS 1200 or any kind of database course, you're probably familiar with that. So it's like a one to many. You have one wait line that can have many different customers simultaneously. The wait line contains the line, and that's the actual queue that we have to interact with. But you also might keep track of number of arrivals, number served, and total time waited that customers have waited in total. And then you may just have one method called simulate. The simulation engine that I worked with, you called a couple methods, but then you just called simulate after you set up all the parameters, which was usually the hard part, that and editing the code. And then when you just wanted it to simulate, you literally called simulate or start, something like that. So lots of simulations work like that. I've worked with other software that does similar things. So once you start the simulation, then it starts randomly going through and deciding whether a customer enters or leaves and things like that. And each customer, independent of the actual wait line, knows an arrival time, transaction time, and a customer number, and the ability to get this data as well. So here is an algorithm for simulate. It's a bit pseudocode-ish, although much of it's very similar to Java. So we have a new customer arriving. If the new customer arrives, increase number of arrivals, set the transaction time. If the customer has a 2-minute transaction or 1-minute transaction or 10-minute transaction. So you do that, you set that transaction time. Next arrival, new customer containing the clock, transaction time, and the customer number, that is number of arrivals, and then you actually enqueue it. If as we're looping through here, if we get to the point where the transaction time, as long as it's greater than 0, you decrement it. But at some point, it's going to get to the point where the transaction time is less than 0. So if the transaction time is greater than 0, if there's a present customer still being served, if the present customer is not still being served, it'll go to this else if. It'll go to the else, and then it'll check this. It'll say as long as the line isn't empty, then I grab the next customer, get the transaction times that are randomized or whatever, and then come back to the top. And then that's the new customer that arrived. Then you take care of that one. Pretty cool. So this goes through and just shows you kind of a visual about it. So first customer arrives, customer number 1 with a 5-minute transaction at time 4, meaning it went down by 1. Customer 1's still there, being served. At time 3, time 2, customer 1 still has 3 minutes to go. Another customer has arrived. That's by randomization. And this one, their number does not go down, you'll notice, as the time ticks away. So each loop iteration in this particular program represents a minute going by. Yeah, minute going by, because this is based on minute transactions. That's why it's a simulation, because it didn't really happen, right? So every time the loop goes by, this one is on 3, then 2, then 1, and then on the next, so by this point we have 3 people in line. The person in queue, or dequeued rather, customer 1 finished and dequeues, departs, and then customer 2 can have their transaction start, and then it goes down from 3 to 1, and then customer 2 finishes and leaves, dequeues. And customer 3 begins, 4 and 5 are still waiting, and then 3 finishes, 4 starts, etc. So it keeps going like that. So again, the wait line itself isn't a queue, but it is composed of a queue. So we said that we're participating in composition or aggregation. It's not one of the big 3 object-oriented principles, but it is actually used at least as much as inheritance and more. So it is important. It's just not considered one of the quote big 3 in order to make your programming language object-oriented. You have to have encapsulation, inheritance, and polymorphism for it to be a truly object-oriented language. So right here, the wait line has the queue interface line. Now you might think, well, wait a minute, why are they creating an interface? Well, they're not. They're creating a reference variable of that interface that actually, when we create the instance, when the wait line is created, it creates a linked queue. Now we haven't seen an implementation, but we know that it can be a linked queue, array queue, what have you. But we've created a queue instance, but it's not an instance of the interface because you can't have an instance of an interface. So we call reset, which resets all the other values as well. All right, simulate goes through and does the exact same thing we were talking about. It's the pseudocode. It's counting down, has a probability of a new arrival here. So based on a probability, if the math.random value that's returned is under that arrival probability, then we make a new arrival, and then it keeps going, enqueuing, and then in this second set of if-else, you notice the first one is not attached to this one. It doesn't have an else here connecting it. So if this one, even if this one is selected or not, we still check these out. Oops. We still check these out right here. Okay, so display results, that's pretty simple, not really having anything to do with the implementation so much. Reset sets everything to 0, empties the queue out using the clear method, right? You could do capital gains. That's another example they do in the book. So I'm not going to spend a lot of time on this, but it's just to say that the queue, the line example, and the capital gains example, a lot of information are in the slides, but also if you refer to the book, you should be able to get a really good grasp on what's going on. So stock ledger, this would be another example here, stock ledger. The implementation again creates a queue instance with the ledger, and then buys and sells, things like that. So it's pretty interesting, and it has to keep track of when did you sell, when did you buy, etc. So it's another simulation. Pretty cool. Java class library does offer an interface called queue. Now it has different versions of the enqueue and dequeue. It has something called add and pull, offer an element, or rather add and I think it's, add and offer, remove and pull, element and peek. That's what it is. So add and offer are alternatives, remove and pull are alternatives, element and peek are alternatives, and then you have is empty and size. Those aren't alternatives. So the reason they offered alternatives is because they made some that return a value and then one that has an exception. So they just wanted to give variable options here. Now, a related topic is the ADT Deque. You'll notice the name of this thing is doubly-ended queue. Now, a lot of people think, oh, double-ended queue, it's like DEQ. Why don't they have QUE? Well, there's a problem there, because that is pronounced DQ, and it represents a method. So it would be even more confusing if we named it Deque and spelled it DEQUEUE, right? So they kind of got clever here, and they just made it one set of UEs instead of two. So this one's a data structure. The other one, DEQUEUE, is a method to remove an element from a queue. So a double-ended queue, or a doubly-ended queue, or a double-ended queue, two different ways of saying it. The Deque, obviously I've been pronouncing it Deque. It's not pronounced a DQ or dequeue or something like that. So has both queue-like operations and stack-like operations. So in some ways it's similar to both. Now what it has in common with the queue is that you can only access at the front and the back, again. However, with a regular queue, it's first in, first out, always. So you add items to the back and remove items or dequeue them from the front. With the Deque, you can actually add or remove from the back or the front. So they give you a little more flexibility. So I'd say this is more flexible than a queue, because you can add to front, but you can also add to back. So add to back's more traditional queue. Add to front is more of a kind of a stack operation. And remove front is both a queue and a stack operation, whereas remove back is not something you do with a regular queue, but you can do with a Deque. And then you have get front and get back, which do not change the structure of the Deque, but they allow you to peek at either the back or the front. Then they give you the interface for the Deque and go through the implementation options and things like that. But I think you get the point. So just know, again, even with the Deque, enqueue, and they actually have enqueue and push. You can do add to front, right? So if this were a stack, it would be looking like this. You'd have stacks adding items to the front or the top, and also stacks removing items from the top. Okay, so the front's kind of like the top. And then the stack, you'll notice on this side, the stack never interacts with another opening. It only interacts with the front or the, quote, top. If this were a queue, so that's how you're supposed to read this, is you're supposed to, one at a time, pretend, oh, you have a Deque, and then excuse the other stuff, like forget it's there. So the queue behaves a certain way. It enqueues. So how do we add items? We enqueue, and we dequeue. We ignore the other stuff. And you could, of course, get front. That's the only other option. I don't know why they didn't put a parenthesis there. I think that's a typo. The other stuff, like the deck, see, I almost did it myself. The deck, you can add to back, and you can also add to front for adding. For removing, you remove from back, remove from front. So it's kind of like a stack and a queue. And retrieve, get front. They both have a get front method, queue and deck. And then get back. That's the one thing that this has that none of the others have. The stack nor the queue has a get back. The stack doesn't interact with the back at all, and the queue never removes anything from the back. It only adds to the back. All right, here's a pseudocode for using a deck to read and display a line of keyboard input. So while not at the end of the line, we keep going, we grab a character. If the character is backspace, we remove that character that was just added. So if you think of someone just typing, and think of this as kind of like maybe the code of the software, the driver that's interacting with the keyboard at a high level, if it detects that the character is a backspace, it removes that character that the previous character, right? So we never actually add the backspace to the stream. What you do is you compare and then remove. If it's not a backspace, you add it to the deck of characters. And then once they're done, once they are done with that line, you display the corrected line. Okay, so if the deck is not empty, print out all the items starting at the beginning, going to the end. So it's pretty cool. So this one independently waits until you get done typing, it looks like, and then hit enter. So, computing capital gains. Okay, not going to go over that again, but it's another technique you can use using a deck instead. But if you're interested in economics or want to double major or maybe minor in economics, knowing little things like this, economics or accounting or business even, would be good to know a little bit about that. So the interface deck is available in the Java class library. So that means this is one you would not have to write yourself. The one in the book is called Deque interface. That one is solely code you would write, whereas this one right here is called Deque, and it's provided for you. So whenever you see Java class library or JCL, they're talking about stuff that Java is already providing for you. If you choose to use it, you can use it. If you don't, you can make your own or use a third party or whatever. The Java class library also contains something called the array deck. Okay, so it's an array implementation of the deck. And then thirdly, we want to talk about the third abstract data type that's queue-like or similar to a queue. This is called a priority queue. So you consider how a hospital assigns a priority to each patient that overrides time at which they arrive. So a regular queue is chronological. If you get in line at a cafeteria, assuming there's no cuts, you have people in the order that they arrived, and they're getting their food, hopefully in that order, right? So that's a regular queue. You can't do this in a hospital situation. If Billy Bob smashed his finger with a hammer and it's starting to hemorrhage a little bit underneath his nail and it just hurts a little bit, you're not going to get Billy Bob in there and then someone comes in with a heart attack and you have to tell the heart attack person to wait because Billy Bob's having his thumb looked at. It doesn't work like that. There's a priority. So that in an ER sense, that's called triage. There's usually a nurse or a paramedic or someone with medical skill that's going to determine if someone needs to go ahead of other people. So there was one time I was having some unusual symptoms where my face was not moving the way it should during a lecture at U of M, which was exciting. It was near the end. And my students were even offering to take me to the ER. And I said, let's finish up the lecture. I think it's Bell's palsy. I don't think it's a stroke. So that's probably not the wisest thing to do. But I did some self-tests. I was pretty sure it was probably just Bell's palsy, which is, we'll get to in a second. But I got to the ER, and they don't mess around. I told them, I said, I think this was Bell's palsy. By that point, my face wasn't working on the left side, but I just want to double, just wanted to come in to check. So they literally rushed me in there, probably ahead of 12 other people that were in there. Some of them had like flu or weren't feeling well or, bashed their finger or had an infection start 6 days ago and waited too long and didn't make an appointment with their regular doctor, so they ended up in the ER. A lot of people do that. So anyway, they took me back, took care of me. That is priority queue in a lot of ways. So it basically organizes objects according to priority, not just chronology. So chronology can play a factor, but severity or priority is used as well. There's the interface, also very similar in some ways. You'll notice this interface extends comparable. It's an interface of T that extends comparable of anything whose superclass is T. You don't really have to worry too much about that stuff unless you plan on taking the Java developer exam or something like that. You might want to look into that, but the regular generic stuff is good enough for our purposes. So public T peak is empty, get size clear. Most of these are pretty much the same as what we expect, but the difference is like this. You have tracking your assignments. If I have a course, task, and a date, the due date is actually going to have an effect, right? So add project, and you also have a course code, task, and due date. And you'll notice that once they start using it, they create the priority queue and then call add on it. But the priority queue is going to take care of it based on due date, probably, is what we're going to do. All right? And, of course, there's a priority queue class available in the Java class library. So it's available to you to use as you see fit, or you can write your own depending on the circumstances and needs. Or extend this one, I suppose. I don't know that it's a final. I'm not sure. Okay. Sorry about that. Implementations. We'll spend a few minutes in this, but I'm not going to do overkill on this. A lot of this is you could refer to it, but be aware of how it works. Give you an idea, maybe. So linked implementation. Obviously, we have links and arrays, right? Those are our primary implementations. We've got the array-based abstract data types and the link-based implementations of the abstract data types, which become data structures. So in this case, a linked implementation of a queue, a really good implementation might be a singly linked list, meaning we only have next pointers in each of these nodes, because you could have a previous pointer, right? And then you could go back and forth if you needed to. That would be called a doubly linked list. But for a regular queue, it's sufficient to have stuff going one direction. However, if we just have first node, if you remember to our bag implementation, it was fine. Bag was fine, and even stack was fine. We just had the node top at the front, right? But with a queue, it's really inefficient every time I want to add an element to have to walk all the way down the list and then add the element to know that I'm at the end, right? Or likewise, if I decide to make this the back, then I would have to add stuff here, but whenever I wanted to remove it, I'd still have to walk down the whole list. It's not like an array where you say jump to index 7 and it's just there. It does not have random access, so you have to walk the list. So the way they overcome this is inside of the queue class. Remember, we're talking two different classes here. One is the linked chain, and one is the queue. Okay? The queue uses or is composed of a linked chain. All right? That's the implementation it's using. So for the queue will maintain a node pointer at the front, and then the last node over here points to the last node. So there's a little bit more effort and a little bit more memory taken inside of the queue implementation, but it's way better, because what happens if we have to add an element to the back? Well, that's pretty easy. The way we do that is we just say, hey, last node, whatever you're pointing to, can you set your next, or set the new nodes, new node to null, and then set the current last node's next to the new node, and then set yourself to that new node. That's how you add an item to the back. And then as you access items and remove them from the front, that item will eventually end up at the front. It's pretty cool. So they make the linked queue here. First and last nodes instead of just one. We have first and last nodes. I think I said there was a linked chain in a queue. I meant there's nodes in a queue, and then the queue forms this linked chain. That's what I meant. So the node is here. The node just represents an individual holder for an entity, piece of data, an entry into this. So a person waiting in line or what have you. That's the enqueue. So the new node gets created at the very beginning. This is if we have an empty queue. new node gets created at the beginning, and first and last are both null. And then after we add it to the actual structure of the queue, we have to have first node point to it and last node point to it. So that's the very first node we add. Subsequent nodes, we have to have before and after adding a new node to the end of the non-empty chain. So if this is the very last node in the queue, at this point, at time A, we have time A and time B. At time A, the new node is not part of the chain yet. It isn't part of the queue. It's just a node chilling out in the heap, right? It doesn't really do anything. It's just sitting there and, smoking some ganj with its friends or something like that. I mean, eating chocolate and pizza. Sorry, it would never do. Nodes never do illicit or non-illicit drugs, neither. So the new node's just chilling here with its buddies, and it's not doing anything. It's not part of the list. And then all of a sudden, right here, the list says, okay, set your next to the new node. That's the first thing it does. And then the next step will be what? I guess, let me ask this. Is this node part of the chain now? Yes. However, is this the last node anymore? This one? No. So it has to update and say last node equals new node. So it said last node dot set next node is this, and then last node equals new node. So it changes what it's pointing to. Because new node, we assume, is a local variable that'll just be used during the adding process, and then it goes away and dies as soon as the method's done being called. The last node pointer, the reference, is persistent throughout the life of the object of the queue. So we need it to keep track of this last node to know where the end is. Get front's easy. If it's empty, we have to say, hey, that's an exception. You can't remove anything from an empty queue. Otherwise, return the node at the front. Very easy. Dequeue, get the front. So that's a little helper right there, get the front. And as we assume that the first node can't be null by this point, get front will be throwing an exception. So this should never be true. So first node, let me say that differently. First node should never be null, is what the case is. If it is, then this would throw an exception, but we should have never gotten here because that should throw an exception. So that's just a little extra insurance. That's why they're using the assertion. But first node set data to null. First node get the next node, right? So we grab front, and that's the actual data. We set the actual node's data to null, so it's not pointing at anything for its data. And then we say first node equals first node's next. So when you do that, remember when we assign this, you're not saying, hey, my node is now your node magically. You're saying my reference to a node is now holding the address of the next node. Does that make sense? So remember, you have to distinguish between the references and primitives. Primitives hold the value directly, and although we interact with references like they're the actual object, like when I do this, it's calling set data on the object, that's for sure. But it's kind of like it's passing it along to the object and saying, hey, call set data. Here, when I say first node equals first node dot get next node is returning the address of a brand new node next in the chain of nodes, and it's reassigning the value of first node, which is the address, because it's a reference, right? That's a common theme throughout this course, throughout any of the Java courses I teach. Difference between references and primitives, and also difference between references and the actual object it's pointing to, okay? So far, so good? So what does the removal look like with this queue? If you have the queue before there's any removal with more than one entry, this is just an example with 4, but it could be many more or even a couple less, what have you. Just more than one is basically the idea. So you've got the first node pointing there, last node pointing there, the data, the entry at the front of the queue and entry at the back. And how do we remove an item? Well, remember with a queue, you remove or dequeue from the front. You enqueue to the back. So to remove this, you set the data to null, like we did previously in the code, and then jump it, basically. You're saying, hey, first node, get me first node's next. So it just basically jumps right there. The front piece of data is going to be returned to the client. It's just the data, and we're actually removing the node by jumping it. then it will be garbage collected. Pretty cool. Okay, so next up, we have the queue of one entry and then removing the entry at the front. If I only have one entry, then the first node, the front, will be again returned to the data. First node and last node will both be set to null. That's basically what's happening. So if it's empty, we would clear it, right? If it's empty, it is doesn't need cleared. But to clear, you just basically set first node and last node to null. It will take care of the whole list. Is empty would be if the first node's null and the last node is null. This would be an example called a circular queue. I won't spend too much time on it, but the idea is that if I have an array, even though we can't really have a circle, the problem with implementing a queue with an array is if I have the front and the back and everything's nice and shiny, but remember the front is shrinking by going this way, and the back is getting bigger by going this way, so you might end up with this situation. So you end up at the front here and the back there, and you've got all this empty space, but it thinks it's full because there's no more room at the back. The way to solve this, or at least one of there's multiple ways to do it that would be a kind of a similar type situation, would be to wrap around. Okay, now then you have to be able to detect, hey, which part is the front, which part is the back, and I don't want to, if I increment the back, mod the size, I should not interact with the front because that would mean it's full. So full queue, actual full queue is when it actually is full, not when everything keeps scooting over and then we eventually think it's full. So that's the whole idea behind the, quote, circular array. It's really a regular array, but we just treat it kind of like it moves in a circle. So then they give you the code with the circular array implementation, and this is the key right here. So that's what I was talking about, the wrapping around the queue and going back to the front. Back index equals back index plus 1, but if we go off the edge, it wraps around. Pretty cool. All right. Keep going, keep going. I think that's the majority of the stuff I had for you. Oh, yeah, I guess the is empty is different for the circular queue. You have to say, is the front index equal to the back plus 1 modulus the queue's length? So that's to make sure that if they are... the back index is 1 away from the front index, mod the queue length, that means that it's full. You can't add anymore. Or I mean, it's empty, rather. I'm sorry, it's empty. So the front index is the back index plus 1 modulus queue length. So the front and the back could be anywhere on the array, and if they get in this position, that's how we know it's empty. There we go. You could also do a circular link implementation. So instead of keeping track of front, you can just cleverly keep track of one node, the last node, in a singly linked list, and then we always know that last node's next is always going to be the front. So this is just one way to cut down on having to use that extra, piece of memory. I would probably sacrifice the memory unless it were a major issue and have 2. It's not even that big. I mean, it's, without compression at the hardware level or the lower levels, it's 64 bits or 8 bytes. I mean, I think it's generally worth it to not have to do the extra calculations, but it really depends on your circumstance. So they're just giving you additional ideas, ways to implement it. Okay, here's the 2-part circular linked chain. They're going through and showing you different options with it. I'm not going to hold you too much to that, but just be aware that they do exist, these circular implementations. And there is an abstract queue library, and there are methods in that interface as well. So we could use the JCL and implement abstract queue if we wanted to. This is a doubly linked deck. Now, notice that the doubly linkage occurs with the nodes. It's not just decks that could have double links, but this does make it easier with the deck. A lot easier. So you'll notice that we are using extra memory because each node no longer has 2 sections like a data and next. It has the data, previous, and next. So the first node's previous is null because this is the first node. And the last node's next is null. But we have this link with the previous and next that we have to maintain as we remove and add items. So that's a little extra work. It does take up a third extra memory at least. So do be aware of that when you try a double linked implementation. So you're sacrificing, sacrificing memory for maybe a few computation cycles, and that could be better to do that. Okay. Also, headache, too. You're saving yourself some headache by using double queue. All right, so that's pretty much that. That's what I have for you on queues and decks and priority queues this week. Thanks a lot.